Hi, did you know that the cosmic microwave background or CMB is actually the afterglow left from the Big Bang? This relic radiation has allowed astronomers to probe the universe just 380,000 years after the Big Bang, basically when the universe was just an infant. In this episode, we'll try to unravel the mysteries of the cosmic microwave background radiation and try to understand their implications for the evolution of the universe at large. Let's begin. The cosmic microwave background is one of the most fascinating remnants of the Big Bang. It is the oldest light we can observe in the universe, dating back to just 380,000 years after the universe came into existence. You can imagine this faint glow to be like static caught by a sensitive radio dish. Although predicted by theories of the early 20th century, this primordial light was accidentally discovered by Arno Penzias and Robert Wilson, two employees of the Bell Telephone Laboratories in the 1960s. Penzias and Wilson were working in the Holmdel horn antenna, which was a radio dish used for satellite communication and radio astronomy. Penzias and Wilson realized that no matter where they pointed the radio dish, a faint signal was always present, even after they cleaned the dish and got rid of the birds nesting in it. The signal was very faint but consistent, so they could not rule it out as noise. They measured the intensity of this signal at a range of frequencies to figure out that it peaked at a wavelength of around 2 millimeters, which corresponds to a black body temperature of 3.5 plus or minus 1 Kelvin. That is, it was coming from something which was very cold, because radiation is always emitted by a source, right? But then how was it possible that this signal was all pervasive? Does that mean that it was coming from the space itself? That is, the empty space between stars and galaxies and everything that's out there? But as we discussed in an earlier video, any object having a temperature essentially implies that it is composed of atoms which are transiting between different energy levels. But the space as we observe it now is pretty empty, right? So where was this signal generated and coming from? To answer that, we'll have to look back at the history of the universe since Big Bang. By the way, did you know that the term Big Bang was coined by cosmologist Fred Hoyle to ridicule the idea of a hot, dense universe? Basically, cosmologists in the early 20th century came up with many different theories of how the universe was born. Based on the fact that we see most of the galaxies moving away from each other, and in the context of Edwin Hubble's observations that the farther a galaxy is, faster it is moving away from us, some of the cosmologists proposed the idea that going back in time, like rewinding a videotape, all this must have started from a single point in space and time known as singularity. Back then, the universe must have been very hot and dense, and at some moment in time, that singularity began to expand and all the matter in the universe began moving as we see it. This period is what cosmologists refer to as inflation. As an analogy, consider a firecracker going off. It is said that in a BBC broadcast talk on radio, Professor Fred Hoyle, who disliked the idea of a hot, dense universe in its initial stages, ridiculed the idea by dismissing it as some sort of a hypothetical Big Bang, and since then, all the theories of cosmology supporting the concept of Big Bang came to be known as the Big Bang cosmologies. Time is the testament that theory survived the ridicule, but the name stuck. Anyways, coming back to the thermal history of the universe. Around 13.8 billion years ago, the universe expanded faster than the speed of light for a fraction of a second. This, as I just told you, is called the period of cosmic inflation. Scientists are not sure what came before inflation or what powered it. Most cosmologists believe that inflation explains many aspects of the universe we observe today. It is possible that inflation may have magnified the naturally occurring differences in the density of matter on very small scales, and traces of which we are observing in the cosmic microwave background. But we'll come to that in a minute. After cosmic inflation, The energy driving it transferred to matter and light in an instant in space and time that we now call the Big Bang. 1 second after the Big Bang, the universe consisted of an extremely hot plasma. You can imagine it like a soup of light and particles having a whooping temperature of 18 billion degrees Fahrenheit or around 10 billion degrees Celsius. The next few minutes marked an era of nucleosynthesis where protons and neutrons collided and produced the earliest elements: hydrogen, helium, and traces of lithium and beryllium. 5 minutes after the Big Bang, most of the helium that we find today had been formed, and along with it, the universe had expanded and cooled enough that no more new elements formed. But even at this point, the universe was still too hot and dense for atomic nuclei of the formed elements to catch electrons and form atoms, because if the density of electrons was too high, they could scatter off the photons. This is often referred to as the universe being opaque to radiation because photons could not travel much before being scattered away into another direction. But all this changed around 380,000 years after the Big Bang, when the universe had cooled enough that atomic nuclei could capture electrons. This period is called the epoch of recombination. Formation of atoms during this time had two major effects on the cosmos. First, with most electrons now bound into atoms, there were no longer enough free ones left to completely scatter light, which sort of cleaned up the cosmic fog. Consequently, the universe became transparent, and for the first time, light could freely travel over great distances. Secondly, the formation of these first atoms produced its own light. In other words, the last surface from which the radiation bounced got encoded in the emitted light that we now observe as the cosmic microwave background. This glow emitted when the universe was at a temperature of around 3000 Kelvin was much hotter earlier but cooled as the universe expanded, and is rightfully called the cosmic microwave background. Cosmic because it is coming from everywhere. Microwave because it now peaks in the microwave region of the electromagnetic spectrum, and background because it is not emitted by any particular object. Cosmic microwave background is the oldest light we can observe in the universe. At the time of emission, it peaked in the near infrared, but the universe has expanded 1100 times its volume since then, and as a result, the wavelength has stretched, sort of like the cosmological redshift, and now peaks in the microwave region at a wavelength of around 2 mm, which corresponds to a much cooler temperature of just 2.75 Kelvin above absolute zero. After the cosmic microwave background, the universe once again became opaque at shorter wavelengths because all those hydrogen atoms absorbed most of the radiation. So, for the next 200 million years, the universe remained dark, and consequently, this period without any shiny stars around is known as the Dark Ages. At this point, the universe consisted of a sea of hydrogen atoms, helium, and trace amounts of heavier elements. But gas was not uniformly distributed throughout the universe. The cooler areas of space were lumpier with denser clouds of gas. And as we have discussed in earlier videos, these clumps grew more massive because their gravity attracted even more matter. As the clouds became denser and more compact, the centers of these clumps became hotter and eventually hot enough to trigger nuclear fusion. These were the first stars. These newborn first stars were 30 to 300 times more massive than our Sun and millions of times brighter. Over the next several 100 million years, the first stars came together to form the first galaxies. Initially, the light from these stars could not travel far because it was scattered by the relatively dense gas surrounding the first stars. Gradually, though, the ultraviolet light emitted by these massive stars broke down the hydrogen atoms in the surrounding gas into their constituent electrons and protons. As this reionization progressed, starlight traveled farther, breaking up even more hydrogen atoms, while the universe expanded and further assisted the progress by naturally lowering the density of the surrounding matter. As a result, by the time the universe was around 1 billion years old, stars and galaxies had transformed nearly all the ambient gas, making the universe transparent to light as we see it today. This period is therefore referred to as the era of reionization. The cosmic microwave background is not just the surface of last scattering for the primordial light, but an experimental proof favoring the Big Bang theory. The reason that the Big Bang theory is so widely accepted today is because if it were true, we expect to observe certain characteristics in the universe. Firstly, the Big Bang predicts that the universe is expanding and all the galaxies are moving away from us with a speed which depends upon how far away the galaxy is. This, as you know, my friends, was shown to be true by Edwin Hubble. Secondly, the Big Bang should produce a characteristic radiation spectrum. Because if the universe was much smaller and hotter in the past than it is now, and if it has been expanding ever since the Big Bang, then it must also have been cooling down this whole time. As an analogy, imagine a gas that expands adiabatically, that is, without changing any heat with its surroundings. If the volume of the gas increases, its temperature must decrease. Therefore, if we know roughly how old the universe is and how fast it is expanding, we can form a pretty good guess of what its current thermodynamic temperature must be. And that is exactly where the measurement probes of the 20th century came in handy. Although the initial experiments to measure such a spectrum began as early as in 1930s, the first major breakthrough came via the observations by the Cosmic Microwave Background Explorer, popularly known as the COBE satellite. COBE measured the CMB over the whole sky and helped establish several facts. Firstly, the cosmic microwave background is almost completely uniform with an almost constant temperature over the whole sky. This, for instance, is the picture of the entire sky where each pixel is color-coded by its temperature in the range 0 to 4 Kelvin. And as you can see, it is pretty constant. However, it is not completely constant. Another set of instruments called the differential microwave radiometers on board the COBE satellite measured the tiny temperature variations between the hot and cold spots on an angular scale of around 7 degrees on the sky. That is represented by this picture here. There are tiny fluctuations, or ripples if you like, in the temperature of the cosmic microwave background at the level of just 1 part in 100,000. For reference, consider that if the Earth's surface was smooth to 1 part in 100,000, the highest mountain would be just 100 meters tall. The theory also predicts that the Big Bang should have produced some simple particles such as hydrogen, helium, and deuterium being the most common in very specific ratios. These ratios are also observed in various studies. As a result, the observed recession of galaxies, the cosmic microwave background radiation, and the abundance of certain light elements form the three pillars of the Big Bang model of cosmology. As of now, no other theory can explain all these three observed phenomena as well as the Big Bang theory can, and that is why it is so widely accepted today. Over the past few decades, many experiments have measured the tiny fluctuations in the cosmic microwave background with accuracies gradually getting better and better. These tiny fluctuations are present because of the tiny variations in the density of the universe immediately after the Big Bang. Since the tiny fluctuations in temperature of the cosmic microwave background, what scientists like to call as anisotropies or anomalies in the temperature, reflect the density fluctuations in the matter at that epoch, the cosmic microwave background radiation helps in predicting the initial conditions which led to the universe we observe today. Any regions which were slightly more dense tended to attract more matter and get even denser and attract even more material. This runaway process guided the formation of the first stars and galaxies and ultimately the clusters and superclusters that we observe. The strength of the signal from these fluctuations is linked to various properties of the universe and help astronomers to determine its age, what it is made up of, and even how it might end. As the measurements get even better, our knowledge of the universe has increased. While the COBE satellite could map the hot and cold spots of about 7 degrees on the sky, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001 and operational until 2010, could zoom into a resolution of better than half a degree. Its successor, the Planck mission, on the other hand, zoomed in even further to 0.16 degrees while observing the microwave sky between 2009 and 2013. All of these missions mapped temperature differences with the precision of 1 part in 100,000 to 1 part in a million. In order to minimize measurement errors related to such small signals, the spacecraft's detectors pointed towards two spots on the sky at the same time and measured the temperature difference between them. The satellite swept the entire sky in this way, and software generated a map of all those tiny differences. Thanks to these CMB probes and many other experiments conducted from the ground and via balloons in the sky, we know the universe began in a Big Bang, and around 380,000 years later, electrons and protons combined, allowing light to move around freely. We know our cosmos is 13.8 billion years old and how fast it is expanding. We know that 31% of the universe is matter, but only about 5% of it is made up of ordinary matter like you and me, while 26% is the invisible dark matter. Most of the rest of the cosmos is composed of a mysterious repulsive dark energy, which forms about 69% of our universe. Scientists have been studying the cosmic microwave background for decades, but it is not an easy task. The signals we receive from the cosmic microwave background are incredibly weak, and they are often drowned out by interference from our own galaxy and the Earth's atmosphere, the stuff often referred to as the foregrounds by cosmologists. It is like trying to hear a whisper in a crowded room. But despite these challenges, researchers have managed to extract some fascinating secrets of the universe from the cosmic microwave background. One of the biggest hurdles in interpreting the CMB is the sheer amount of data involved. We are talking about millions of pixels of data, each containing a wealth of information about the universe. It's like trying to find a needle in a haystack, except that in this case, the haystack itself is made up of tiny needles. And even when we do find a pattern or anomaly, it is often very hard to distinguish it from simple statistical noise. Another challenge is the fact that the cosmic microwave background is a snapshot of the universe when it was just a baby. It is a two-dimensional map of the universe in its infancy, but it is not a direct observation of the universe as it exists today. And therefore, it takes a lot of cleverly applied mathematics and modeling to get it right. The cosmic microwave background is a reminder that the universe is full of mysteries waiting to be uncovered. It is a testament to the power of human curiosity and the importance of continuing to explore and study the cosmos. The CMB may be a relic of the past, but it is also a window into the future of our understanding of the universe as we observe it today and to what it will evolve into tomorrow. I hope you enjoyed this episode. Please do like, share, and subscribe to the astronomy class, and share your feedback with us in the comment section, because that is the only way we know how you are liking our content. I will see you next week. Until then, take care.